Hey everybody, welcome back. I don't know where everybody is, but there's enough of us to get started. Uh. Last time I taught this, I went straight through textbook order, but I don't know that that's the best order. So we're actually gonna start with 5.4. Which teaches sigma notation, actually gives tools for developing the ideas we do in previous sections. And they kind of gloss over it like it's going, we're gonna cover it later. Sigma notation, it allows us to compactly write summations. Right, a sum of terms. Or a summation. In a compact form. Basically, we could have, the notation goes something like this. K equals 0 to n. And I'm just gonna list it as a sub k, where this is the. A sub k is the kth thing to add up. So this actually means a sub 1 plus a sub 2 plus a sub k plus a sub n minus 1 plus a sub n. This crazy letter right here, this is actually the Greek letter sigma. It's the capital version of sigma. And that's why it's called sigma notation. For example, if I go with k equals 1 to 4. What this means is this is the number to start with. And this is the last number. And if I said k squared. This is really 1 squared plus 2 squared plus 3 squared plus 4 squared. 1 plus 4 plus 9 plus 16 is 30.
So we're just basically, we're taking k, we're plugging whatever number it gives and we're plugging it into the k, and then it's going from that number to
And we
the
keep
one on
going up
top.
by 1, yeah, all the way up to the top. So whatever this, we're replacing the letter K here with what we start with the first number. And we go up in the sequence, adding 1, not like a half or anything, but adding 1 until we get to the top of it. If you use Microsoft Excel. Like the spreadsheet and like. When you want to add up a column, this is the only character it shows. There's just a giant E on the fucking toolbar. And you put it right below the column of your numbers, like the empty square right below all the squares above it that are filled with numbers. Put your cursor there, you click E and fucking add all that shit up, super easy. This letter right here is called the index of summation. The most common ones you will see are I, J, K, and N. Most common starting values are 0 and 1. So if it's new to you, it's a new notation, a new way of writing, adding stuff up. You will use it a lot down the calculus sequence, when you get to calculus 2. There's an entire like chapter that uses this a lot. This is just motivating what we're gonna do in chapter 5. Let's take a look at another example. Let's go with I equals 0 to 5 of 3i. So this would be 3 times 0 plus 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. Now, we could multiply them all right away, or every single one of those has a 3, and I can factor the 3 out. And make this a little quicker, only have to multiply once. And that adds up to 3 times 15, which is 45. Notice that this, if I write this in sigma notation. Is I equals 0 to 5, just I. And we just had a 3 out front, multiplying by it. That equaled I equals 0 to 5 of 3i. So constants. We say constant coefficients. Can be factored out. Outside the summation. If you guys want to try. short, so it doesn't take too long, just practices the ideas. Did I just come up with another one that adds to 45? I'm crazy, that was chance. What if I had one like this? I don't have a K present, right? But I do have something I can keep adding. I can add 3, that's the K equals 1 time. Plus 3, that's the K equals 2 time. And then we go up to the K equals 6 time. This is 3 times 6, we're adding it up. Repeated addition is just multiplication, which is 18. So in general, a general form of this is if we have K equals 1 to N of some constant number C. The result is just C times N. They can trick you with this shit. K equals 1 to 4 of 10x. We see the x, we think variable. But this is constant in terms of x. So it's just gonna be 10x times 4, C times N, 40x. It's sneaky. But they might try to, I don't know if they have any problems like that in the homework or not. But it's just also designed to make you pay attention. You gotta make sure that the letter matches.
Jones, on the first one. Where we had the 5n cubed.
Mhm.
Would we be able to factor out a 5 in all scenarios with an like a 5n cubed like that?
We could have written this as 5 n equals 0 to 2 of n cubed.
Because obviously, like in this case, you still get 45 if you have 8 and 1 added together.
Yeah,
But like in other scenarios where you might have something different, do you think it's just better just to play it out like that when you have a cube? Instead of
I
turning
did
back?
it because it was a cube and it like, as soon as you start, like, I stopped at 2 for a reason.
Mhm.
You start getting into bigger numbers and people find it more difficult to cube shit in their head.
Okay.
I figured everyone could handle up to 2 cubed in their head just fine. 3 cubed doable, but it starts taking you longer to like do it. You're like, alright, 3 times 3 is 9, times 3 is 27. That one's not too bad, 4 starts fucking with people. 4 squared is easy, 16 times 4 takes a little longer in your head, 64, but. That's why I kept it low. You could have factored it 5 to 5 out. Alright, next example. And we'll look at this a couple ways. N equals 2 to 5. 2 to the n minus 1. So if I do this, I have 2 to the 2 minus 1. Plus 2 to the 3 minus 1. Plus 2 to the 4 minus 1. Plus 2 to the 5 minus 1. So you're gonna get 2 plus 4 plus 8 plus 16. 30. And sometimes we'll have the index. Like the n, but it's subtracted or something. Something you can do, this is. A handy tool. I can say k equals n minus 1. So that I'm doing 2 to k, the k power. That way it's less work to think about. If you do, you have to recalculate. The start and stop. So what I mean by that is take the n equals 2. K equals 2 minus 1, which is 1. So k will start at 1 now. And you literally are just taking these values and plugging them into your formula. For n equals 5, I'm gonna plug it in for the n, 5 minus 1 is 4. And we keep doing that. You'll notice we still get the same terms. But there's less middle steps. And while it took an extra second to do it in the beginning, if you have enough terms, this actually saves you a lot of time and effort. Just by, it's called re-indexing. Another reason this is helpful is because some of the formulas. That you work with require starting at 0 or 1. Some start at 0, some start at 1, and there's a formula set up. So that like, rather than like, if you had like K going from 1 to 100. That's a lot of things to do by hand, but there's a formula shortcut to like figure some stuff out, as we'll cover in a second. Something else to note. Plural for index. Is indices. Doesn't look anything like it. You might, if you're reading something that says indices, you'll be like, what the fuck is that? Return notes. Let's do. K equals 1. And I'm gonna say n equals 4 right here. Just so we don't have to write a bunch of them, but I want you to know that it does work through n, stuff like that. Let's say we had a sub k plus b sub k. Well, this is a1 plus b1, that's my k equals 1 term. Plus a2 plus, oops. e2. It's k equals 2. Plus a3 plus b3. Plus a4 plus b4. And keep going up to n. If n is a different value. But what I'm gonna do is I'm gonna take all the a's and put them together. And I'm gonna take all the b's. These are all added, so this is completely valid, just I'm rearranging the order. Write it like this. But this is k equals 1 to 4 of a sub k. And this is k equals 1 to 4 of b sub k. So in general. K equals 1 to n of a sub k plus b sub k. Can be split into two summations. This actually works with the minus version as well. And we'll just do a shorthand example of that. K equals 1 to 3. A sub k minus b sub k. A1 minus B1 plus A2 minus B2 plus A3 minus B3. Group the A's together. Group the B's together. That is k equals 1 to 3 of a sub k. I'm gonna factor out the minus on this before I do that part of the summation. Got a busy day of grading tests tomorrow.
You don't have classes on Fridays? Is that the only day you don't have classes?
Some semesters I do, cause like, some semesters I'll teach we have our computer science classes on Friday afternoons. Deliberately, like I chose the time slot, no one wanted to teach on Friday at first. But I chose it to be right before FNL, Friday Night Labs. It's a Mesa program where you go do fun shit on Friday night. Do engineering projects, they bring out a 3D printer, sticker machine, all sorts of fun shit. Soldering iron, they do projects and I put it right before that so that students could leave the computer science class and then go right directly over, it's right next door. And me and Professor John Redden take turns teaching it. Alright, so this combines kind of well. With like having coefficients. If I had C1. A sub k plus C2 B sub k. That splits in, I pull out the C sub 1. And I make an A sub k summation. And then I pull out the C sub 2 and I make a B sub k summation. And we'll do an example with this in a second.
C1 and C2 be separate values?
Yeah, they
Okay.
can be, that's why I gave them different numbers,
Okay.
they don't have to be the same number.
Cause then essentially it would just be. It'd just be C times AK plus BK, and then it would just basically be the same thing, you just factor out the C.
Right, if it was the same value, I would just put it all up front and put parentheses around it. Show you guys an example. Let's do, we'll keep the values small. K equals 1 to 3. Let's see. 2n squared. Minus 3n plus 4.
That BK, or are we doing it?
Susan. Thank you. Yeah, looks like, and what do I get trap? That's the wrong letter. I'm trying to avoid using K. I've been teaching like. This section in Calc 2. For like the last 2 or 3 weeks that uses this sigma notation. And I have noticed that if I get writing fast, my K's can look like X's and it's confusing as fuck. So I'm trying to avoid using K's. You know, they look close. If you're writing fast, the K can look a little crooked. And the X can look a little flat. So I can treat each of these as separate things. I would have 2 times n equals 1 to 3 of n squared. Minus 3 times n equals 1 to 3 of n. Plus 4. Or plus the summation of n equals 1 to 3 of 4. Again, it may not seem like a big help, but that we're only doing n equals 1 to 3. But you're going to a larger number, factoring out that 2 and only have to multiplying it once. Save you time. This is 2 times 1 squared. Plus 2 squared plus 3 squared. Minus 3 times 1 plus 2 plus 3. And we had the formula for that already. This was plus 4 times 3. This was C times n. This is 14. So when I multiply by 2, I get 28. Minus 18. Plus 12 is 22. Now, the reason for doing this. I have things that are just in terms of single index. There are formulas for stuff like this. By factoring out the constant and by separating them into different summations, you can take advantage of the formulas. So we have ones for n squared, n cubed. I'll start off with the N one. Uh, I'm gonna say we're going from I equals. 1 to N of I. This ends up being N times N plus 1 over 2. And you're like, what? I can do a derivation of this one fairly quickly. So if I do the I could do 1 plus 2 plus 3 plus 4 plus I plus N minus 2 plus N minus 1 plus N. Now I'm gonna do it in the opposite order. N plus N minus 1 plus N minus 2. Plus 3 plus 2 plus 1. What I'm gonna do is I'm gonna add vertically. This adds up to N plus 1. This adds up to N plus 1. This adds up to N plus 1. Come down here, we have the same thing down here. They're all N plus 1. There was 1, 2, 3, 4, I up to N of these. There is N times N plus 1 right there. But this is adding up the index twice. We added it twice. So we divide by 2 to get back to the original. Yeah, I equals 1 to N. I is N times N plus 1 over 2. There's a famous story in like I forget who it was, it's in the math textbook, some fucking prodigy back in like, I don't know, 1600s, one of the people that came up with all this shit. I think it was Gauss, I think. He was like a fucking kid, and the teacher tried to give them busy work, and he said, add up the numbers 1 to 100. And he fucking had it done in like a minute. Just came up with this idea himself, like. Just out of nowhere, just fucking, I'm gonna speed this shit up. I got the number super quick, and he got beat for it. Spanked or hit with a ruler, or whatever, that, punishment they did. For cheating, basically. But we just came up with the form, it's kinda a fun story. Don't be too smart for your own britches.
Yeah, 'cause if it's 1 to 100, you have 101 for like.
Yeah,
High
yeah,
calculus.
101, and there's 100 of them. 100 divided by 2 is 50, so 50 times 101 is 50. You did it super quick. Cause having 101, you're just ones and zeros that you're multiplying by, it's quick math if you know multiplication. And he was a super smart person. I wanna say he was like 7 or 8, he's fucking doing this shit. I don't know how old he was though. Alright, there's a couple more, but. I'm not gonna derive them, I'm just gonna make a list of the formulas we've had so far. We have had. K equals 1 to N of C equals C times N. We did K equals 1 to N of C A K. I'm back to K again. I need to get rid of my K. This can be done as C times K equals 1 to N base of K. As long as I don't have X's on the right, and none of these formulas have X's. We saw that a combination of these can be split into two different ones. And I'm writing the plus and minus version at the same time. The one I just showed you. And some other ones that we have. K equals 1 to N of K squared. I can't imagine deriving this as any fun. I haven't tried it. It's N times N plus 1 times 2N plus 1 over 6.
That because they multiply the N into the N plus 1 and then took derivative
Say what?
for the 2N plus 1? Is it because they multiplied the N into the N plus 1 to get
You know, they might have done derivatives or intervals on this. Yeah, we haven't talked about intervals yet. I'll play around with that today after class and see if that's where they came up with it. You can take derivatives of these. You'll do it in Calc 2. This is called, they're called power series, and you'll take the derivative to speed up stuff. Yeah, there's a one for N cubed. K cubed. And it actually looks like the first one, but it's squared. I bet it is done with integral derivatives. So this is kind of like N squared times N plus 1 squared over 4 if you wanted it in a different form. Okay. So those are kind of like the formulas we'll have here. Let's do an example where we have to do a little bit of thought and work. Yeah, I'll keep that on the same page right here. Let's say we have. I equals 5 to 15. Of 2i minus 3. Now. This can be sped up pretty well. If I have a different starting number. If I can get this restarted with 1. I can use those summation formulas we have above. So this is where it's a good idea to re-index. Let's re-index to starting at 1. So how can I go about doing this? I wanna restart, like, let's say I wanna have an n equals 1 to start with. What does this gotta do, what do I gotta do with the I to get there? I gotta subtract 4, right? Five minus 4 would get us down to 1. Better way of writing that is n equals I minus 4. Would give us a 1. I equals 5. If I equals 15. N equals I minus 4. We gotta keep the same pattern. Would take us down to 15 minus 4 is 11. What does this do to my I here? I have n equals I minus 4. If I add 4 to both sides. I get I equals n plus 4. So I can re-index this to start at 1 going up to 11. I just have to replace I with n plus 4. So before I do anything with that, I'm gonna clean that up. That's 2n plus 8 minus 3. Which is 2n plus 5. We'll take a break after this problem. Let's just get through it. Everyone go with what we've done so far. Does it make sense? This is the trickiest part, re-indexing, I know, takes practice. Now after this, it's just formulas. I'm gonna split this up so that I put the coefficients outside. And then I can take advantage of our formulas. That's the n plus 1 or n times n plus 1 over 2. This is the Cn. So I'll have 2 times 11 times 11 plus 1 over 2. Plus 5 times 11. The 2's will cancel out. And we have 11 times 12. Plus 5 times 11. This is 132 and 55. Which is 187. If you don't know the shortcut to multiplying by 11. Like I did that pretty quick in my head, 11 times 12 is 132. Like the shortcut to multiplying by 11. If you have 11 times 12. This is 12 times 10 plus 1. Right? 12 times 10 is 120. 12 times 1 is 12. And I'm adding these up, I have 132. The key is you take the 12, you split it. And you put the number between them. You add the two numbers that you had to get between them. So like 11 times 27 is 297. I'm not multiplying, I am literally splitting that and adding the two numbers. It only gets a little trickier when they add to a number that's bigger than 10, then you gotta like stop and think about it. Like if I did 11 times. I don't know, 38. What happens is you have the 380 plus 38, doing the 10 times 1 is 418. So if I wanted to split it, the 3, the 8, I have 11 in the middle, I have to add that extra 1 to there. To get the 418. Personally, I think at this point, it's easier to split it to 10 times 10 and 1 and add those two. And I can do that for most things without a calculator. Because multiplying by 10 and 1. You're not doing anything, you're either keeping the same number or adding a 0 to it. That's how the summation stuff will work, let's take a 10-minute break. Alright, so now we continue and we get to, how does this segue into calculus? So. What we're gonna be looking at is we have like a function f of x. Has graph. And it is desirable. In many circumstances. To be able to find the area below the curve. Between A and B. So that's A, this is like f of A. Over here we'll have B and f of B. As you can imagine, we don't have a formula that like just can find this general area here because it's not a shape that we have a formula for. It's not a rectangle, it's not a square, it's not a triangle. But this is what we can do. We can break it up into a bunch of tiny pieces. And we try to keep the pieces the same width. And each of these we make smaller regions. There's a couple strategies. One strategy involves using the left endpoint for each square. And making a rectangle with it. Or that box. And when we have a rectangle is really easy. Rectangle, the area. Is length times width. Now you'll notice, if I do that, this is, in this case. Adding a little extra each time. Because that part is not part of the function. And when I do it over here. So this is all added, it's extra. Over here, it's not counting this part. It's missing this because we're using the left endpoint. So depending on it, whether it's curved up or it's curved down. Changes whether or not it's including it. But the idea is if we break up the rectangle small enough. That extra or missing area. Gets reduced. And we can get a good approximation by adding rectangles. I'm going to try to simulate the 3 different common ways that are done. You actually learn better methods in Calc 2. But the beginning methods are kind of easy. Let's say this is all the same bit. Let's say this is a width delta x. So like this left endpoint is like x sub I. And this is x sub I plus 1, which is x sub I plus delta x. And we're gonna do that on each of these. This will be xi, this is xi plus 1, xi plus 1. So this could be any rectangle within the like the thing, just picking out a rectangle. We saw the left endpoint. This is the left method. there is a method that uses the right endpoint going up xi plus 1 and coming to the left. That gets excluded with the right one. This is extra with the left one. And they have one that we do the midpoint. We find like halfway between these. We come up to here. And we make our rectangle at that height. Where we have some extra here. Some missing here. And it balances out better. A better balance. The extra and missing kind of balance. Counter each other. Not perfectly, they're not exactly equal to each other, but it does reduce the mistake. This is the idea of what we're doing, now to lead that into the sigma notation kind of idea. But I think if I really take the time to show the rectangles on here, you'll like totally get where we're going with this. Give everybody a chance to finish drawing that. There is one more idea I'm gonna do for the sigma. So let's take that little bit of curve. I'm gonna make it a big section. Let's say that's like xi and xi plus 1. If I do this, the left endpoint. A lot of extra. When the width is big. And the width of rectangles is large. Now I'm gonna make smaller rectangles. And do the same left endpoint thing. And color in a little bit of extra with green here. Notice that the smaller rectangles. Generate. Less total error. The little rectangles only have the filled in green. Doing the full width of the big rectangle has the green and the red. It's a lot less. Does that make sense? We don't wanna have all that extra area. We want our area to be plus. The point of doing this is to find the area. So if we have a lot of area, this is shitty. So we want to, the goal will be to make the. Rectangles as narrow as possible. Reducing the error even. Reducing the error the most. Does that track? Okay, so with that in mind, what we do. We break this up into a bunch of rectangles. So this is like x0, x1, x2, x3, x4, x5, x6, x7, and x8. Making 1, 2, 3, 4, 5, 6, 7, 8. N equals 8 rectangles. I'm gonna do N equals 8 just for the example here. Cause you can see it. Now, if we're adding up these rectangles, adding up allows us to do summation. So we want to add up the areas. From I equals 1 to N. Does that make sense? Everybody on board with that idea to find the get the area underneath the line? Well, the area of each rectangle is the length times the width, so we need to figure out what those are in terms of the picture. We're gonna call each width delta X. If we keep it the same width on each of them, we can call them each delta X. So that'll be our width, delta X. And we can figure out what it is if we take the total length. And divide by N. Does that make sense? We're breaking it up into N rectangles, so we divide it by N and we should get the width of each rectangle. Well, the total length, if we're going from A to B. Is B minus A over N, that's delta X. So that's my width. What's the length of the rectangle? Just like It's the height, right? It's the height. And what is the height? It's f of x, right? But it's a different x, so maybe like. Xi? And I'm gonna say xi star. And the reason why I use the star is because we saw. Depending on. Using left endpoint. Right endpoint or midpoint. This height changes. So it depends on which strategy we take. Pick up again. Guys ready? So let's look at an example here. I'm gonna say this is like x zero. And we go distance delta x. This is x zero plus delta x, which is x1. And then we go another distance delta x. This is x zero plus two delta x, which is x2. Another delta x. X zero plus three delta x, x3. And we keep going up to xn. Will be x zero plus n delta x. And I'm just gonna use this fairly straight line. Well, I ran out of a straight line. And let's look at what adding up the right endpoint would look like. So the first rectangle is like f of x naught plus delta x times delta x. That's like our k equals 1 rectangle. And then we got for our next rectangle, f of x naught plus 2 delta x times delta x, k equals 2. And I do the next one, f of x naught plus 3 delta x times delta x. That's k equals 3. It looks like I can call if I want to do f of x sub k star. The x sub k star is x naught plus k delta x. Does that look like that tracks, that makes sense? Notice that this is like k equals 1 right there. K equals 2 right there. K equals 3 right there. And I'm trying to like rename each of these things. So the right endpoint formula is a summation of I equals 1 to n. F of x sub 0 plus I delta x times delta x. Which, after we replace delta x, b minus a over n times b minus a over n. Because delta x was b minus a over n. It turns out if you do this same process for the left endpoint. X sub I star ends up being x naught plus k minus 1 delta x. And so you get I equals 1 to n. F of x naught. Plus k minus 1. Times, not k, I. B minus a over n times b minus a over n. This is gonna make a whole lot more sense when we plug it into an example, which we'll do next. Ready for a quick example? Let's take a look at like y equals 3x. From 0 to 4. Let's make it 0 to 6. Should go up to 18. And let's do like n equals 3. And we'll do the shitty one, the formula that had like the left endpoint. So we want to find that area. Now this is easy. We know what that area is. It's area equals 1/2 base times height. Which is 1/2 times 6 times 18. Which is 54. We're gonna see how close the right hand or left hand approach works. If I break this up into 3 rectangles. And we're doing the left endpoint, like there's literally no. This is the actual area we're getting. So we can see it's gonna be off. Right? I used a small n just so we could show how the formula works. So we need to look at our delta x. Our delta x is b minus a over n. We went from 0 to 6, so this is 6 minus 0 over 3. Delta x is 2. So we're doing k equals 1 to 3, that's my n. Of f. Of x naught plus k minus 1. Times, this is my delta x right here. And then times the delta x. This is doing x naught. Plus 2 times k minus 1. Times 2. And x naught is my starting point. So this cleans up even more. I'll say 2k minus 2 distributing, and then I got a 2. What was f of x though? F of x was 3x. So if I'm replacing this inside the x, I have k equals 1 to 3 of 3 times 2k minus 2 times 2. This is 6k times another 2, that's a 12k. 6 times 2k is 12k minus 12. Break that up. Oops. Remember, this was n times n plus 1 over 2. This was c times n. So this is 12, n is 3 here. So 3 times 3 plus 1 is 4 over 2. Minus 12, which was my c times 3. This is 6 times 12 minus 36. Ends up being 36. I'm gonna rewrite this delta x as 6 over n, because if we change n. Make smaller rectangles, this gets better, right? That's what we talked about on the last page. Having bigger rectangles, which means more n. Gets us a better approximation. So. We had n equals 3 rectangles. What if we use the limit as n goes to infinity? We have our delta x is b minus a over n. Which means delta x, the width approaches 0. We have infinity on the bottom. It approaches 0. But we get a good approximation and we can do the limit stuff. So delta x was 6 over n. F of x was 3x. And we still have that formula right there, we can see. We're gonna do the limit as n equals 1 to infinity. Of f of 0, that was our x naught. Wait, I need a summation in here. F of 0 plus k minus 1 times 6 over n, that's my delta x. And then I had another delta x on the outside, 6 over n. Wait, I made that look like shit. Limit as n approaches infinity, there we go. Limit as n approaches infinity. K equals 1 to n. This is 3 times the k minus 1 times looks like 6 over n times another 6 over n. Three times 6 is 108. Alright. So this has limit as n goes to infinity. K equals 1 to n. I have 108 over n squared times k minus 1. This is constant for in terms of k. So which means we can pull it out front. Everyone okay with that so far? I just multiplied the 3, the 6, the 6, they're all, this is all multiplied together. That's 108. We have n squared on bottom. We pulled that all out because it doesn't have a k, and then I rewrote that split. This had the formula n times n plus 1/2. And this had the formula c times n, which is 1 times n, which is just n. So this is limit as n goes to infinity. I have 108 over n squared. Times n squared plus n/2. Minus 108 over n squared times n. (108) divided by 2 is 54. So this, I can split this up, this is 54 n squared over n squared. Plus 54 n over n squared. Minus 108 n over n squared. After we reduce some or simplify. The limit here is just 54, right? That goes to 0. That goes to 0 because n is going to infinity on bottom. And wasn't that the area we calculated using the triangle formula? So this approach works. It gets a lot easier. We're gonna do different notation, we're gonna dump the limit shit. But I want you to see where the idea comes from. So like, just know this is how it works, but like. Everything after this, when we do finding the area below the curve. Is way loads easier when I work with like the same way derivatives got easier when we switch to using formulas. Finding the area is gonna get easier, it's called integration. That's where we're gonna start. What is it? Thursday, next Tuesday. Don't forget, Monday is Veterans Day, so you have classes on Monday, don't show up, because your teacher ain't gonna be here. Have a good day. Peace. ETFO.